Assalamualaikum warahmatullahi wabarakatuh. We are from Group 18 and we will present about High Performance Liquid Chromatography HPLC. Now, I will introduce you our group members Hasha Amni, Nur Ain Atirah, Nurin Hanani, Putri Alisha, and me, Nur Alia.
Hi, so let me explain about HPLC. High Performance Liquid Chromatography is analytical technique used for separation of compound. In theory, this is technique that allow efficient separation of the component mixture. Stationary phase is spiked in HPLC column, then mobile phase will go through the column under high pressure. Next, the principle of HPLC. It will start with injecting the solute, which is stationary phase, on top of the column, and separation will occur when the solute and mobile phase are pumped through the column. Then the separate component will elute as peak on the result known as chromatogram. So for the application of HPLC, it can be used for any compound that can be solute in liquid as mobile phase, such as analysis of sugar, pesticide residue, organic acid, lipids, amino acid, toxin, vitamin, and so on. We move on to the objective of this experiment. The first objective is to determine the retention time of a standard solution, which will be caffeine. The second one is to identify the caffeine peak in a soft drink sample. The last one is to determine the amount of caffeine in soft drink sample using the response factor method.
So now I will be explaining about the procedure. So for the first one, we have caffeine standard solution, where we need to prepare two solutions, which is solution A, stock solution, solution B, working solution. For solution A, which is stock solution, first step is to weigh 10 mg caffeine into a 10 ml volumetric flask. Step 2 is to dissolve it with distilled water, and step 3, fill the distilled water until calibration mark. Next, the solution B, which is the working solution. For step 1, we need to pipette 1 ml of solution A into 10 ml volumetric flask. Step 2 is to fill it with distilled water till reach calibration mark. Next, sample preparation. For the step 1, we need to pour 10 ml of soft drink sample into a small beaker. Step 2, use a magnetic stirrer to remove any carbonation. For step 3, we need to filter 2 to 5 ml aliquot through a 0.45 mm pore diameter membrane filter to remove particulate matter. So this is the block diagram of HPLC, where I will be explaining the function of each component. So for the first one, we have HPLC solvent. It is a glass container that holds the solvent or the mobile phase. Next, HPLC pump. It is a device that delivers the solvent through the system at a constant pressure and speed. So next, we have injector. It is a device that introduces the sample into the mobile phase. Next, HPLC column. It is a stationary phase that separates the sample components. Next, we have a detector. It is a device that measures the separated compounds. For the last one, we have data acquisition. It is a device that records the data from the detector.
First, let's examine the caffeine standard chromatogram. Here, we see a single dominant peak with a retention time of 2.482 minutes. This peak corresponds to the pure caffeine, as expected since the standard contains no other components. The area under the peak is 6,249.49 AU seconds, representing 100% of the chromatogram. This data will serve as our reference point for identifying and quantifying caffeine in the other samples. Next, let's look at the chromatogram for Coke. Unlike the standard, this sample shows multiple peaks indicating a mixture of compounds. The most prominent peak is at retention time of 2.481 minutes with an area of 7,281.12 AU seconds, making up to 57.36% of the total chromatogram. This peak is consistent with caffeine standard, confirming the presence of caffeine in Coke as the primary component. Other peaks, such as those at 1.948 minutes with 19.43% of the area and 2.031 minutes with 2.11% of the area, represents additional compounds, likely additives or other ingredients unique to the formulation of Coke. Finally, let's analyze the chromatogram for Levita. Similar to Coke, Levita has multiple peaks indicating a complex mixture of the compounds. The dominant peaks appears at 2.799 minutes with an area of 5,978.82 AU seconds, accounting for 49.68% of the total area. This peak is most likely caffeine as its retention time is close to the standard. Other significant peaks include those at 2.019 minutes with 23.80% of the total area and 2.219 minutes with 9.86% of the area, representing additional components in Levita. These peaks collectively contribute to the remaining 50.32% of the total area, reflecting the complex formulation of the mixture with caffeine as the major component.
Next, for the calculation, we have to calculate the response factor RF for the given standard. In order to calculate the conversion factor, we have to use the formula of RF equals to peak area of caffeine over concentration of caffeine standard. Conversion factor, which is 1 mg/ml, equals to 1000 ppm. From the data that we obtain from the result, response factor can be calculated by dividing the peak area of caffeine from the data and divide with the concentration of caffeine standard, which is 1000 ppm. For caffeine standard from the result, which is 6249.49 over 0.9 mg/ml, and at the end we would get the answer for 62494.94 mg/ml, and that's for caffeine standard. Next, in order to calculate the concentration of caffeine in soft drink sample, the first sample we have is Coke. So now the first step is dividing the peak area caffeine in sample over RF, which is response factor that we get from caffeine standard earlier. So by following the formula for Coke that we obtained is 7001.12 over 62494.90 mg/ml. And then we could get 0.1120 mg/ml. And then the next step, convert them into ppm by times it with 1000 ppm over 1 mg/ml. So it's gonna be like this: 0.1120 mg/ml times 1000 ppm over 1 mg/ml. So the answer that we obtain is 112 ppm. That's for Coke. Lastly, for the concentration of caffeine in soft drink sample number 2, which is Levita, the steps are same with Coke, dividing the peak area caffeine in sample over RF, which is response factor. So from Levita that we obtained from the results, 11151.10 over 62494.90 mg/ml, and then we could get 0.1784 mg/ml, and then times them with ppm in order to convert them. So it would be like this: 0.1784 mg/ml times 1000 ppm over 1 mg/ml, and then the answer would be 178.4 ppm. And that's all for the concentration of samples. Now, moving on to the discussion of this presentation. Hplc, High Performance Liquid Chromatography, is a broad analytical chemistry technique used to separate compounds in chemical mixture. These separations utilize the pressure-driven flow of a mobile phase through a column pack with a stationary phase. And there is two types of Hplc, which is reverse phase Hplc and normal phase Hplc. Reverse phase Hplc is the most commonly employed Hplc technique, while normal phase Hplc employs a polar stationary phase and a non-polar mobile phase. For a good separation and accurate result, this experiment has applied the gassing system. The purpose of the system is to remove dissolved gases and dust from the liquid to ensure a more accurate result. And then the presence of bubbles and dust will cause performance interferences. Lastly, the gassing is accomplished in several ways by vacuum pump or sparging with an inert gas. So we could discuss that the key properties for this experiment or presentation by observing the particle size, viscosity, column temperature, and flow rate. For particle size, the smaller the particle size, the better the resolution. Secondly, for viscosity, lower viscosity results in efficient resolution. And for column temperature, the higher the column temperature, the faster the speed of elution. And lastly, for flow rate, the lower the flow rate, the better the resolution. Gas chromatography, GC, and high-performance liquid chromatography, HPLC, are both powerful analytical techniques used to separate, identify, and quantify components in a mixture. However, they differ in terms of their principles, applications, and suitable analytes. That's all for the discussion of this presentation. Caffeine's retention period in a standard solution was effectively ascertained, offering a starting point for study. The presence of caffeine in the soft drink samples was established by identifying and comparing its caffeine peak to the standard. Furthermore, the response factor approach was used to quantify the amount of caffeine in the soft drink, demonstrating the efficacy of the analytical procedure used. Overall, the study's goals were met, demonstrating the effectiveness of test techniques in determining caffeine's level. We hope you enjoyed our video. That's all from us. Goodbye and thank you for your attention.